Hi, everybody. I'm here today with Melissa and Dave. Melissa and Dave are mechanical engineers at MCW Consultants, and I am Marine, a passive house designer and certifier at RDH Building Science. Today, Melissa, Dave, and I will talk about the lessons learned around the electrification of the student residence and commercial kitchen typology. Okay, so we'll start with setting the scene before diving into each challenge individually. So, institutional kitchens, the challenges. Let's start with some context to start with. So the typology that we're looking at, the student residence, is really a large residential building with a commercial kitchen. We need to future-proof that typology. So what are the drivers towards future-proofing? We know that in Canada, especially, we have a lot of legislations towards net zero carbon buildings. We have the carbon tax ramping up pretty fast. In Canadian dollars, we are at $50 per ton this year. We're going to ramp up to 170 by 2030 and probably all the way to $300 per ton in the future. So quite a big driver. We also have climate mitigation, resiliency against extreme events or future predicted climate. So really a lot of drivers to get this typology right. So what are the exact challenges into future-proofing that typology? Well, to get a low operational energy building to start with, the commercial kitchen and the equipment themselves will be the key challenge, right? Getting that energy use intensity, that EUI down. But if we then look at a low operational building, making that building an all-electric building, including a pretty large kitchen and residence domestic hot water demand, is what will be key into cutting the greenhouse gas emissions down, labeled as GHGI. So we've been pretty fortunate as a team to work on making this a reality. The project is the University of Toronto Scarborough Passive House Residence, and we are using that project today as a case study to illustrate our process and sharing the lessons learned. So that project is really leading the way in terms of large student residence with the commercial kitchen typology. So what is this project? 9-story building with a basement. We have the large commercial kitchen around level 1. And then we have a few communal spaces at level 2 and level 3 till 9 being fully residential to host about 750 beds. So quite the undertaking. I'm going to take a moment to recognize the whole team. Funnily enough, we had a fairly unusual delivery method on this project. We had a compliance team that prepared the design up to 100% design development, and then a design build team led by the contractor, Pomelo, to deliver the building from 100% DD till completion. So on the compliance team, you have Handel Architect, Core Architects, Integral, Stephen Winter, RWDI, and Jablonski. And the design build team is led by Pomelo with IBI, MCW, EXP, and RDH. So before diving into the challenges, I wanted to highlight the performance targets that we've achieved. This is a passive house project, so you'll be familiar with the targets on the screen. Starting with the space heating demand, we have a target at 15 kilowatt hour per square meter per year, and we are currently sitting at 14 kilowatt hour per square meter per year. So we're good on that one. Regarding the primary energy renewable target, we had a limit at 132 kilowatt hour per square meter per year with a limit of 100 only on the residential portion. And the performance that we're achieving at the moment is bang on to the 132 kilowatt hour per square meter per year for the combined building and 88 on the residential tower alone. So you can see that the residential tower is a little bit better and the podium with the commercial kitchen is a little worse than anticipated. More importantly, I wanted to share the industry targets because these are very passive house specific targets, but we need to be able to relate to the industry and speak the same language. So in terms of EUI, energy use intensity, we are achieving an EUI of 109 kilowatt hour per square meter per year, including the commercial kitchen, which is pretty good, and 72 on the residential tower alone. So pretty good results there. And translating this into the greenhouse gas intensity figures, we have a total at 5.4 kilograms of CO2 per square meter per year with the combined building, going down to 3.6 kilograms of CO2 per square meter per year for the residential tower alone. So you can see that the figures that are on the screen are definitely figures of high performance buildings that are future-proof to meet upcoming legislations. Diving into the challenges finally. So they are different challenges when we dive into a commercial kitchen. First and foremost, it's kitchen equipment. We'll dive into this a little bit more as the presentation progresses. The second one is really around ventilation. So we have large exhaust requirements highlighted in pink on the screen, but that exhaust requirement has to be balanced with makeup air in blue on the screen. But that makeup air coming directly from outside has to be preconditioned, preheated in the winter. And that is what is taking a significant portion of our energy budget, right? Remember that space heating demand includes ventilation loads. So that is really a big impact on tour space heating demand. So zooming back, we really have equipment as challenge number one, as well as ventilation, which is grouping all these items under that second challenge. It keeps going. We have a bit more. The third one being around the domestic hot water demand. So you can see on the screen, the size of the circles are descriptive of the load that is associated with them. And the showers in the residential portion is clearly accounting for a lot of it, but the kitchen is not negligible at 7,000 liters per day to deliver the 2,000 mils per day that we're after, as well as other items on the suites and the podium part. And so we're going to have to ask ourselves, how do we meet that demand in the most efficient way? And through that presentation, we will look at all these strategies, be it reduce, then recover using waste heat, as well as electrifying that domestic hot water load. Okay, so diving into the details. We're going to start with kitchen equipment and the call for efficient kitchen equipment. That challenge is really touching on two aspects towards future-proofing, which is really the total energy demand that we have, so the EUI, as well as the electrification, because I'm sure, as most of you know, kitchen equipments are not necessarily all electric by default. I'm going to start with the energy use intensity, the EUI, the energy consumption aspect of it. The first question is, by how much are we going to reduce the energy consumption that is associated with the kitchen? So we needed a starting point. We didn't have a lot of benchmarking, but we found through one of the SIPSI guides out of the UK, some benchmarks around 4 to 5 kilowatt hour per meal. This is a final energy metric, the energy at the meter. And for a passive house commercial kitchen, we need to carve this down significantly. By how much? Well, we were lucky to have a precedent through the University of Victoria student housing projects, for which a lot of back and forth had happened, and allowances for the kitchen were made. You can see them on the screen. The allowance is 1 kilowatt hour per hot meal, 0.25 per cold meal, which means that based on your project specific hot to cold meal split, you will end up somewhere in the 0.65 to 0.85 kilowatt hour per meal additional allowance to capture the energy of that kitchen. And so through that significant reduction, this is really how you're lowering your building energy consumption. So how are we going to do that? Well, I'm not going to lie, this is fairly new and unique, and we don't have a lot of data, be it from the calculation side as well as the monitoring side. So to take a very safe approach, we followed both qualitative and quantitative approaches at the same time. The qualitative approach is really about the use of industry best practices for commercial kitchens, as well as the quantitative approach being, you know, line by line, equipment by equipment review to understand what is the impact associated with each piece of equipment. And one thing I want to highlight before moving on to the best practices is that cannot happen. This calculation, that understanding cannot happen without having a clear idea of the predicted kitchen use, right? We need to understand the kitchen profiles, be it food prep, equipment use, occupancy, kitchen staff. Without that, without a good level of granularity going from the bottom up, that fine tuning of the kitchen design is a little bit difficult to achieve. So let's look at best practices, which were all implemented at UTSC. No open coolers. We don't have any, we don't have any air curtains. We all have display fridges with doors on them. Then for the larger walk-in fridges and freezers, they have to be not only highly insulated, but also with continuous insulation. So we're talking about the 6 faces, including the floor part, to be fully insulated of these walk-in fridges and freezers, which means that has an impact on the slab design, as you can see on the top right-hand corner. We also need good airtight and insulated doors to be used very cleverly to make sure that the environment in the walk-in fridges and freezers is well maintained. And then the last 2 are really related to the equipment themselves. So we would use induction-based kitchen equipment as much as we can. And for other type of equipments, we would really use high performance ones. So we're talking about, skillets and kettles with lids rather than without them, use of combi ovens with a condensate hoods rather than none of them. And even, simply enough, using a 4-slice toaster rather than a rotary toaster, which keeps going on and on, right? So every little helps. This is how we carve down the total energy consumption. Now, I want to touch base on the electrification piece, because carving down the energy consumption is one part, but the electrification of it, meaning completely giving up gas, is a very different aspect. So how did we approach this? We started by looking at the pieces of equipment with the largest energy consumption. You can see them listed on the screen. And it took a lot of research, a lot of back and forth, a lot of calling suppliers and manufacturers to understand if electrically based equipment were available and if we were able to use them on this project. But we managed to get all these equipment on electricity rather than gas, even the big ones like fryers and boilers. So that was a pretty good win as a start. Funnily enough, the last item that caused us some trouble was the pizza oven. This was the last kitchen equipment left on gas. And right now, I want to give some kudos to the University of Toronto, because their staff themselves went to different restaurants with, which had electrical pizza ovens, to talk with a chef, test and taste the pizzas, and all of this to come back to us and say, yes, we're good. We can get that final equipment off gas and deliver an all-electric building. So again, I want to highlight that none of this could happen without a really good integration between every single party, be it the design team, as well as the client team and their kitchen staff. But thanks to that, we do have an all-electric kitchen, which is amazing. And this is the way to really reduce your greenhouse gas emissions. So we've talked about equipment. Now moving on to the next challenge, which is really about bad ventilation loads, as we mentioned at the start. And that particular challenge is the only one that is 100% directed to that space heating demand criteria, right? The space heating demand criteria looks at the enclosure as well as the ventilation heat losses. So until we find a way to carve that kitchen ventilation load down, or space heating demand is really struggling and not going under the 15 kilowatt hour per square meter per year mark. So what are the different strategies that we are using? The first set of strategies at the top is really around kitchen layout and kitchen design. We've mentioned the use of induction cooktops, moving away, so thinking about the layout, moving away from island stations and making sure we're having high efficiency, high capture hoods. This is item number one, approach number one to reducing that demand, but we're going to go further with demand control ventilation, with the use of unconditioned air, we'll see how, and then finally meeting the remaining demand with some heat recovery in the middle. So let's dive into the details of each of these strategies one by one over the next few slides. First and foremost, I mentioned kitchen layout and kitchen design, and it is almost unbelievable how much of an impact we can have simply by rethinking and fine-tuning the kitchen layout. How do we approach that? Well, using, first of all, induction and more efficient equipment, which means that the environment that is created need less exhaust to be maintained under good conditions. But number two, grouping all appliances that have the same cooking schedule rather than having them split between different cooking stations. So grouping them together, as well as number three, putting the equipment with the highest exhaust requirement in the middle, and then adding to the sides equipment with lower and lower exhaust requirements, which means that as a whole, for your cooking station in each corner, you can reduce the overall ventilation exhaust and still achieve the service that you're after. We can go even further and removing island stations. Quick example on the screen, we achieved at UTSC a 46% reduction in exhaust requirements by moving the pasta station from an island setup to against the wall setup. So big and not costing anything with a bit of care in the layout. We went further with, now that these stations are grouped together, we still want to judge how far away the cooking surface is from the hood, as well as the good use of wing walls, right? Like additional wings that would protect, that would guide the exhaust requirement. And finally, the use of high capture efficiency hoods. You see a few drawings on the side. And by combining all of these 6 principles together, we've been able to achieve a 26% reduction in exhaust flow rates at UTSC, carving it down from 11,000 CFM all the way down to about 8,000. So quite a lot. And all of this simply with care around the layout and planning of the kitchen. So just a quick slide on the high capture hoods and how do they function. You can see on the left that a hood will typically capture what is behind that blue half circle. And all the portion, the orangey portion on the right is missed. The plume is escaping. And if we are trying to capture that, we need to increase our exhaust flow rates. In a position, you can see on the right how high capture hoods will function with that use of an air curtain in effect, which is described in blue, and that is pushing all your cooking air at the back of the hood and being captured more efficiently. So you are capturing a lot more of that ventilation without increasing your flow rate. So again, a very good approach to reducing that exhaust requirement, which reduces consequently our ventilation load. Moving on to approach number 2, now that we've reduced the maximum exhaust requirements, we're going to add the demand control system. What is it? It's, as the name describes it, making sure that the ventilation associated with the kitchen is happening on demand rather than all the time, even if it wasn't needed. So you would have some clever algorithm guiding that system and looking at different sensors to understand how much ventilation is required. So these sensors could be temperature sensors in ducts, it could be temperature sensors within the room, as well as, I find this fairly clever, infrared sensors, looking at your cooking surface to understand at what stage of your cooking process you're at. So very, very clever. Does this help? It really helps a lot because the demand control ventilation is going to carve down 30% of your overall energy consumption by working on average around 75% of the max exhaust requirement. This is showed more visually in the bottom graph where you see the orange line, which is describing your max. So this is how your kitchen ventilation would function if you had no demand control ventilation system. And the blue curve is actually when the ventilation is working with a demand control system. So you can see the benefits that these systems have. Moving on to approach number 3, the use of unconditioned air. So this was a very clever approach by MCW where the makeup air that is coming in is actually split into 2 different streams. The first stream would be in green on the screen, and that stream will be conditioned because that air is distributed to the space and for the people, so therefore we need to make sure that the temperature is adequate. However, the second stream is needed only for kitchen exhaust. So if we guide that stream directly to the kitchen hood as an air curtain and extracted back again, you do not need to condition that air. By doing so, not only you are specifying or using the right exhaust flow rates that you need for your kitchen to function adequately, but you are significantly carving down the amount of supply flow rate that needs to be conditioned. And that conditioned supply air is what cost us some of our energy budget for a space heating demand. And I can happily say that for UTSC, we managed to carve that supply flow rate down by 53% with this approach. So again, another big win without which it would probably not have been possible to keep our space heating demand under 15 kilowatt hour per square meter per year.
Thank you, Maureen. So again, I'm Melissa. I work on the mechanical engineering side of this project. And up until now, we've been talking about different strategies to reduce our kitchen makeup air load as much as possible. But some makeup air is always going to be needed. So one way to reduce this load is to recover heat from the exhaust airstream. Now, that's not a new idea. So in a traditional system, we're going to be having a heat recovery coil in the exhaust airstream. Once you have heat recovery coil, you also need some sort of fluid flowing through that coil. So we're going to need a circulating pump. On top of that, our heat recovery coil is going to be inside of the duct, which means we need an increased fan static pressure all year round. So there's clearly some drawbacks to this system. First of all, this is a seasonal energy recovery system only, so it's only functioning in the winter. We have that fan energy pendency all year round, and grease buildup on those heating coils is really going to reduce your efficiency over time. So on top of all of that, this is only sort of a stage 1 of heating, and you still require supplementary heat. So clearly the system has some drawbacks, and we're going to show you what we did as we move forward. So our project is just a little bit different. So as you can see, we have what's basically a duct inside of a duct system. So what we're having is passive heat recovery across all of the common duct surfaces. There's no airstream heat recovery devices required. There's nothing inside of those ducts, which means that we have less grease buildup issues. We don't need to increase our fan static pressure. Now, There is still some increase to fan static pressure in the system, but it's significantly less than in that heat recovery coil system. We also have no pumps. And this is all energy that once you put that into the passive house model, it has a significantly reduced impact compared to that traditional system. As we talked about before, that other system is also seasonal. So in this system, our duct in a duct is going to be there all year. So what happens in the summer? In the summer, it looks a little bit counterintuitive because basically you have hot air coming in from the kitchen and you have hot air coming in from outside. That hot air from outside is going to get heated even more as it passes through this duct, and you're going to have an increased load on your kitchen makeup air unit. So, like I said, this seems a little bit counterintuitive, but I'm going to pass this off to Dave and he'll explain why this system does make sense.
Thank you, Melissa. I'm Dave MacKeracher. I'm here to talk a bit more about the challenges and some of the ways we've gotten around them. This next piece I'm going to talk about is how we've managed to reduce that domestic hot water load in the system using a couple of very novel heat recovery devices. So we talked a bit about that duct-in-duct arrangement. Now, in the summertime, what we do is we've actually increased the cooling load on that makeup air unit to the kitchen. And through our heat pump chiller, our heat pump arrangement, that heat pump is one of the primary heating sources that we have for our domestic hot water load within the building. And by increasing the cooling load on that coil, what we've managed to do is transfer that heat through the heat pump arrangement and reject all of that heat back into the domestic hot water system. So that piece that seemed counterintuitive has actually resulted in us recovering that same heat that would have been thrown out and returned it back to the domestic hot water system. So that begs the question, what are, within the passive house framework, what are the other waste heat energy sources available that we might consider recovering? So the big one, and the sort of low-hanging fruit that we identified early on, was the collection of warm and relatively clean shower water drainage from the resident suites. And what we've done is we've collected them in this insulated underground cistern, where that water is collected over the course of the day or over the course of the morning. We collect that and we pump it through this gray water heat exchanger prior to it being discharged to the main building sanitary drain. Now, by pumping it through that heat exchanger, what we managed to do is we've created a cooling load for our heat pump arrangement. And again, extracting that heat out of that drainage water before, but by extracting that heat, what we've managed to do is reject it back into the domestic hot water loop. What that's done is we've now produced a COP of 4.3, and what that means is for every unit of energy that we put into that heat pump, we get 4.3 times that amount of energy back out in the form of domestic hot water heat. So similarly in winter, we have this same heat recovery system. However, that air handling unit is no longer in need of a cooling load. Its primary requirement is heat. And what we've done is we are using that domestic hot water heat to provide, to supplement the heat necessary to maintain the temperature in that air handling unit. That is supplementing the heat that's already been recovered through that duct-in-duct kitchen system. So we have two means of recovering that heat or to temper that heat. One is through the gray water system directly. So instead of pumping through, or in addition to pumping through that heat exchanger, we have the opportunity of taking that gray water and pumping it through this second heat exchanger, which would produce sufficient heat to temper that water further. Or alternatively, we could be using the domestic hot water as the heat source to temper that air. We believe that the domestic hot water loop will be the more dominant energy efficient source for this, simply because of that 4.3 COP. However, we through the commissioning process, we will be determining which way that will go. So, quantifying our heat recovery. So through our modeling, what we found that the COP of the heat pump alone is 4.3, but when we include that free waste heat recovery, that COP climbs up to 5.2. So on average, our domestic hot water heat recovery is 43%, which is which has been a massive boost to us achieving our energy targets for the Passive House project.
Thank you, Dave. So I'm going to pick this back up. Now, we've discussed what our system looks like, but now we want to give you some numbers. So first of all, as discussed, the COP of that heat pump is 4.3. Now, that's looking at that heat pump alone. So, the specified COP. But once you account for the fact that we're using free waste heat in this system, that COP actually climbs to 5.2. So once you consider this overall system, what we're doing is we're using free waste heat to produce domestic hot water for our building. Now, what we did was we found out that average annual consumption over the whole year of domestic hot water, 43% of that is going to be covered by waste heat from now on. And of course, that means that 57% of it is going to be accounted for separately using an electric domestic hot water heater. But that 43% is free waste heat that otherwise would have been, rejected to atmosphere. So far we've talked about a kitchen makeup air unit. We've talked about waste streams from the student residence showers. Now we want to talk about one more system in the building. So what we really want to do is consider every single waste heat stream in the building. And like I said, we've covered 2 so far, and we said this is a passive house model. Let's look at every little bit counts. So we realized that we were also needing to reject heat from our laundry room. Could we possibly capture this for reuse? What we realized was that, in fact, we could. So our student laundry room uses heat pump dryers. So these are ventless. There's no air being exhausted from the space, and there's no air that needs to be made up other than, simple ventilation requirements from ASHRAE 62.1. So our heat pump dryer rejects heat straight to the laundry room. And we have a local fan coil terminal unit in the space that's going to be, collecting that heat from the laundry room and rejecting it to our system. So we're ejecting that heat straight through that heat pump, and then again, we're using it to preheat domestic hot water. So one thing that we had just mentioned is that those laundry room dryers are now heat pump dryers, which are electrified. Now, one thing we did want to bring up is that we had a very difficult time actually specifying ventless heat pump dryers that were, commercial grade, that had Canadian approval. We found a local distributor, and there were really, really few market options. There is, in fact, one viable option when we got to the end of this. So that's something that would have to be considered in future buildings, is that, that process might be difficult, but in the future, we're hoping that there will be more and more options available from different manufacturers. All right, so far we've covered, several different components of our system, but of course, this is a short presentation. We can't cover everything. So some other design considerations in the system that you'd have to account for are what happens when our waste heat recovery system generates too much domestic hot water. Where does that domestic hot water go? How is that heat rejected? one other thing you have to consider is the main electric domestic hot water source. So as discussed, 43% of our domestic hot water is coming from these waste heat streams, but you still need an electric or other domestic hot water heat generation system to account for the rest of that heat. So, there are different options available. We went with an electric domestic hot water system, but that's something that has to be considered. As well, if depending on the system that you go with, you may need some backup electric heat on top of that.
Thanks, Melissa. Thanks, Dave. Before leaving you today, we wanted to wrap all the lessons learned into a couple of key bullet points. We're going to start with the best practices. What do we need to do to future-proof these buildings and that typology in particular? First, looking at kitchen equipment, it's really care into kitchen design, right? These best practice designs to take care of the total energy consumption, as well as, again, great care into the specification of all electric appliances to carve down that time the greenhouse gas emissions. The second point is around kitchen ventilation. We know that this was one of the biggest loads, and that has a direct impact onto our space heating demand, which as a consequence also impacts our EUI and our greenhouse gas intensity. And so what do we have around here? Good care around the layout, the use of demand control ventilation to make sure that we only have ventilation as needed, the clever use of unconditioned makeup air directly to the kitchen hood so that we do not preheat air that does not need that preheating. And finally, meeting the reduced demand with some heat recovery. Finally, regarding domestic hot water, we are for sure going to reduce the load, but a load is still going to be there. So how do we meet it more efficiently? It's really looking at that use of waste heat available in the building, which carves down your EUI, as well as electrification. So finding an all-electric source for your domestic hot water to help us carve these greenhouse gas emissions. Moving on, what were the key lessons out of that, that process? Well, what I want to say is that I think the main barrier today to delivering high performance and all electric buildings, for me, it's really the process, the way we design buildings rather than the technology. So how do we help change that process? We start with one, question the status quo. We're really going to question everything and confirm that our basis of design is valid, not because we've simply done it this way for the last 30 years. Second, we do need a deep client and design team engagement. We need that collaborative process, that integrated design with consultant. There is no way we can find design and cost and performance optimization without that collaborative process. Third, zooming in onto the delivery of high-performance commercial kitchen, you need that deep understanding of what is happening on the ground. You need to understand food preparation. You need to understand kitchen staff. You need to understand how that kitchen is predicted to be used, right? Without that, there is no way we can fine-tune to the level that we've done on this project and get that energy consumption down. And finally, regarding that domestic hot water load, the question is really around that synergy between waste heat rejection and the actual demand. We have to find creative ways of reusing the waste heat that is available. So first, starting with the understanding of what waste heat sources are available, and are they, is it possible to harness them? And all of these aspects together will really help us lower down our space heating demand or total building energy consumption, as well as electrify these buildings to carve down these greenhouse gas emissions. With all of that, this is how we get to future-proof this building, especially that typology in particular. So thank you everybody for listening, and I look forward with Melissa and Dave to taking all your questions. Thank you.
Hi everybody, thanks for being here this afternoon. I hope you enjoyed the presentation. I am here today with Dave and Melissa to pick up on some of our remaining questions. So I think we've been working hard at answering all the questions, but keep firing them away in the chat. I think we've answered all of them, but feel free if you need more details to drop us a line here. Caleb, I want to follow up on your last comment about how do we get all this information down to smaller kitchen operations, because the synergies are pretty amazing in these large ones. So Dave, feel free to add up as I keep mentioning, keep talking about this, but I do think that the synergies are best almost the bigger the kitchen, because we have started to work on slightly smaller kitchens, and some of these best practice approaches at a certain point with the kitchen size start not making so much sense. So I do think that starting from the bigger ones have been extremely good, but we might have a little bit more work to do to see if we can reach the same level of efficiency and synergy on the kind of medium to small size.
Let me pick up on that. The whole concept of that duct and duct, I mean, you would be making up air to a smaller commercial kitchen, similar to a large commercial kitchen that we have at the university project. But the concept of having that makeup air duct run through the exterior of the exhaust duct, that doesn't go away. I mean, you would still see some amount of heat recovery. What you would have to sort of weigh the options of would be how much heat transfer you could get with the exposed surface area of that smaller duct. It's a calculation that you would have to go through in order to see what benefit you get, and then make a business decision whether or not commercially it makes sense.
Yeah, agreed. Sorry, I'm just seeing the questions. Dave and Melissa, I'm going to push this one to you while I think about Monty's questions, as I might need a few more seconds. So Chuck is asking, did you look at using waste heat from the building space cooling system? I think we touched on that. Yeah.
Waste heat, yeah, sure. So the waste heat from the building cooling system. So all of the building exhaust is taken out through the makeup air units. There are 6 ERV makeup air units on the building. There's 4 that serve the student residents, and there are 4 that serve the 2 that serve the podium. And the only one, the only fan, the only air handling unit that's not picked up, or the only ventilation air that is not passed through that ERV is that kitchen exhaust system. So in the podium, for example, the air that serves the dining room, that all goes back to, it's transferred back to the kitchen. It's an open space, and it's used as the makeup air for the kitchen exhaust. So it gets picked up through that passive that passive system that was described in the video. There are a number of other spaces on the podium. There's some classrooms. There's the main entrance lobby. That air, that ventilation air, is picked up through the main, transferred to the main washrooms. There's a washroom groups. There's several washroom groups on the ground floor, and that air is transferred back through those washrooms, and again passes back through that ERV. There's also a basement, and that basement is similar to the ground floor. Also passes, the exhaust for the basement passes through. There's some showers there down there. There's also some washrooms down there, and again that ventilation air passes back through the ERV through via the kitchen exhaust, the toilet exhaust system down there. I guess in order to answer the question more succinctly, we looked at all the energy sources that we could recover it from, and we did our best to try and recover anything that was possible to be recovered.
Yeah, there was, I can attest, there was a lot of outside of the box thinking that was totally needed to get us exactly where we are today, because we are, this is an all-electric building, and based on the performance metrics we were given, we're just in line with everything we want to be in line. So we needed all these approaches to be combined together to get us to where we are today. So definitely didn't leave any stone unturned, I think, on this one. I am going to pick up on Monty's question, which was a really good one. So what are the key similarities and differences between the University of Victoria and the University of Toronto project, and kitchen in particular, I'm thinking? So for sure, as Dave mentioned before, it's the same science behind it. So the same concept, the same best practices do apply. So I think that there are a lot more similarities than there are differences. However, I think summarizing the differences that we're seeing, I think the three key bullet points that I can, think of the top of my head. First, the heat recovery system. So UVic uses a more traditional, runaround coil to move the heat between the two streams, right? Fresh air and exhaust on the kitchen. Whereas UTSC, as you've seen, has that very, bespoke duct-in-duct approach. So different here, but still serving the same concept. The second is the approach around, once you've done all the kitchen layout, guards, like all the kind of no-cost best practice approaches for reducing your ventilation load. The third one is looking at where you can still air from. So UVic is based on a cascading approach. We have several spaces that are adjacent, and rather than bringing all the air from outside to balance the exhaust requirement, we were using some of the cascade air. Whereas in UTSC, that approach of just saying, well, part of it doesn't even need to be conditioned. It can go straight to the hood, no conditioning at all, gets, supplied to the hood and extracted directly again. So we don't effectively pay any energy penalty except the fan running, but no conditioning of that air, has been brilliant, because that has had an even bigger impact on the overall building performance than the cascading approach. And the third one was the point I was referring to at the beginning. So the UVic kitchen is a lot bigger. To give you the sense, between the two, UVic is upward of like 9,000-10,000 mils a day, whereas UTSC is around the 2,000-2,500 mils a day. And so some of the approaches that made sense at UVic were not implemented at UTSC. I'm thinking in particular for the refrigeration system. So for the UVic building residences, the kitchen is so big that we were able to have the refrigeration system, so fridges, like walk-in fridges and freezers, with a separate compressor that was linked to a common loop where the waste heat would help preheat the domestic hot water. For UTSC, the sizes of the fridges, the number, didn't make financial sense to then trying to get them all onto that one system and then recover some of that heat. So again, the few subtleties around, the size and at, when each measure makes sense on these different sizes. And I think we've started to figure it out on the very, very big, but the challenge now is going to be to keep reducing and see how many of these measures we can keep. So very interesting work. Dave, Melissa, I'm going to throw you one more. I see Louis' follow-up question. So for the duct-in-a-duct approach on the heat exchanger, she's asking, is there a minimum space around the inner duct that you need to maintain for cleaning?
Yes, the inner duct is actually the commercial kitchen exhaust duct. It's an NFPA 96 duct. And I can't remember the spacing requirements, but there are in NFPA 96 requirements. Certainly at every bend, you have to put in I believe, an access door to clean the grease out of the inside of the duct. So we have mirrored on the outside of the duct, which is where the outdoor air plenum is. We have mirrored on the outside of that duct similar access doors or similar location access doors through that outdoor air plenum to access the inner cleaning duct. Now, if your question is about the minimum distance between the outdoor air plenum and the kitchen exhaust duct, there is no minimum distance. However, in our calculations, we played around with that distance, and as that distance gets smaller, the velocity through that annular space gets higher, and the rate of heat transfer actually goes up. However, there's a corresponding increase in pressure drop on the fans that we had to account for as well. Generally speaking, at least with this design, 6 inches, I think, was the number that we kept around the kitchen exhaust duct between the outdoor air intake and the kitchen exhaust. And that number worked out quite well for us in terms of the amount of heat transfer versus the fan energy that was used to draw the air through that. I think that was probably what the question meant.
Louis, you can give us a thumbs up if that answers that one. Dave, I'm putting you on the spot too, but I'm wondering, would you be able to give the audience a feel about, the sizing of the ducting and the length of the ducting and the performance associated with it, just to, give them a bit more of a concrete?
Okay, so the sizing of the duct, I believe, and I'm going off of memory right now, was a 40-inch by 20-inch kitchen exhaust duct. That would be the inner duct. And then it would have been a 46-inch by 26-inch outer duct. And the length that we had in the contact area between those two air streams, I believe, was 60 feet. And the rate of temperature rise we got off of that, I believe the Toronto design condition is essentially -10 Fahrenheit, and we got that up to I believe 18 degrees. So there was a 28-degree pickup in that 60 feet of duct. So again, I mean, the sort of higher the velocity, the higher the heat transfer rate, but it's a bit of diminishing returns. Where the real value came in was actually, if the longer you can keep that in contact, that surface area, was actually the bigger driver in that. I mean, if we could have made it longer, we would have, but there were certain physical limitations that prevented us from extending the length of that duct and duct arrangement. I mean, if I could have made it 100 feet, we would have probably picked up another 5 or 6 degrees on that system.
Yeah. And I think in terms of comparison, again, I think that the performance that we calculated after a lot of back and forth was very close to the runaround coils that we're working with, right? So we're also achieving what we were expecting rather than, a significant difference in performance, right?
Correct, but we didn't have the added penalty of the fan energy that we would have had to have overcome with the coils and the pump, the runaround circuit with the pump. All of that would have sunk us on our energy model, quite frankly.
Correct. I was
well,
wearing,
you know better than the rest of us, Marina, how tight that was. Yeah.
My teddy hat, so I was really thinking thermal. But you're right that on the overall they all add up. Okay, there's a couple more questions into your bespoke ducting duct, so I'll keep throwing them your way. Nicasio is asking, how is the area of the inner duct accounted in sizing the exhaust hood duct?
That's just a traditional kitchen exhaust duct system. The exhaust volume is dictated by the kitchen hood manufacturer. I think in our case it was 15,000 CFM total on the system. Again, don't quote me on that number as being exact, but our design would have been somewhere between 1,500 and 2,000 feet per minute through that duct, and that's generally how that size was established. And again, we would look at that size and that aspect ratio, duct aspect ratio, in determining the capacity of the kitchen exhaust fan, and again, even the fan static energy required by that kitchen fan that it would have needed to overcome.
Okay, makes sense. And I think maybe your final one on the ducting duct. Chuck is asking, was this one field fabricated or prefabricated?
It was the whole thing was prefabricated and assembled in the field. So the mechanical contractor came to the site with essentially 20-foot lengths of steel duct. The kitchen duct was steel duct, so it was welded together on site, and then it was hung. And then there was this prefabricated galvanized sheet metal section that came, and it sort of wrapped around that. And it incorporated some holes or some grommets to allow for the kitchen hangers to pass through it and for it to be insulated. There is going to be a fairly rigorous in situ pressure testing of that ductwork to make sure that there's no leakage in the kitchen duct, and again in the exhaust duct, in the outdoor duct as well, to make sure that we don't see any
leakage,
the compromising of that seal, of those seals.
Yeah. Okay, makes sense. Okay. I think there's a quick question from Enrique that I want to touch on quickly around the plume and the high capture. High efficiency capture hood. So plume is actually what comes from the cooking, where we're cooking. And so the goal is that plume should get captured through the exhaust rather than left, alone, greasy, full of moisture, and impacting the indoor environment of the kitchen staff. So the high efficiency capture hood work with almost like the one we presented today. The proprietary system from Halton works with some kind of air curtain that is almost directing the plume at the back of the cooking station, which makes sure that with reduced exhaust flow rate, we are actually capturing most of that plume compared to more standard systems, which would either have a much lower efficiency or would require a much higher exhaust flow rate, which would have a penalty on the energy side to get the same efficiency, to deliver the same service. So this is what we were talking about in the presentation. Let me have a quick look. I think we're getting close to 4:30. So Dave and Melissa, I might want to just throw in a bit of a tough question to leave us with. We're delivering an all-electric building and an all-electric kitchen as a new building for the University of Toronto. What do you foresee the main barriers to be for existing buildings, for existing institutional clients?
Ooh, that's an easy one. Not as hard as you might think. So the all-electric options tend to be using low-grade heat from heat pump systems in order to generate temperatures. I mean, we can do it. That's the most efficient way of generating the heat, because we get COPs, 2.5, 3, 4, 5, depending on the system arrangement. but the heat that we get out of that is fairly low-grade heat. And the problems that we've had in some of our decarbonization projects in existing buildings that have been using 160, 180 degree Fahrenheit water to heat their building, now we are limited with 130 degree water off the heat pump as typically the highest temperature that we can get. Is how we go about either supplementing that 130 degree water with additional heating during the highest heating periods, either with electric boilers where the existing infrastructure cannot accommodate that lower temperature, or in some cases we have actually gone in and we have changed air handling unit coils to bigger surface area coils that can accommodate the lower grade or the lower temperature waters. It's a bit more expensive, but typically right now, a lot of the projects that we're seeing for these decarbonization are institutional types, hospitals, schools, where there is some government funding to back this up. We haven't seen an awful lot of this in the public sector yet, but it is coming. There are some incentive money that's being made available to help some of these, some of the private developers integrate that type of system into the existing facilities.
Yeah, I hear you. And I think that on the enclosure side, which also helps into reducing demand to start with, that we have done enough of that to know that by, tackling both, we should get, you should get pretty close to a plan towards your, net zero energy, net zero carbon building that, at least some regulations and municipalities in Canada are driving us to very, very soon, and also some, regions in the States, even if it's not everywhere, we are seeing a lot of people driving really fast to that end goal. So just understanding that we do have the tools, we do have, the tools and experience to get us there. So it's encouraging. I'm just hoping that we're going to see a lot more of that in the coming years. Okay, I see we're just past 4:30, so I'm going to say thank you very much to everybody. Thank you, Dave. Thank you, Melissa, for joining us today and for the presentation. Thank you, everybody online. I do hope you enjoyed it, and I am very much looking forward to seeing some of you in person next week, okay? Okay, thank you very much. Have a good afternoon. Bye.